All right, welcome to part 2 of today's lecture. This part will focus on sets and logic, so let's jump right in. So if you see that little notation up there, A is a subset of B, that means A is a proper subset of B. If there's no underline under the C, if there is an underline, that means it could be equal to, but we don't know for sure. So it's very similar to less than or equal to sign. It's just is a subset or is a strict subset. So we often call a proper subset a strict subset. So here's a warning. This notation is not universally agreed upon. Many authors use A as a proper subset of B to mean that A is any subset of B, so they might not use the underline at all. And some of those authors then use the notation like they cross out the underline if they want it to mean it's a proper subset of B. But don't worry about that for this book, for this class, or for the set theory class that's coming up. It'll all be consistent. So another warning is that concepts and notation can get kind of confusing. For example, if we have the set of, if we have A, capital A, is defined to be the set of 1 and 2 and 3, then it is correct to say that 1 is an element of A, and that the set of 1 is a subset of A. In notation, we'd say that 1 is an element of A, and the set of 1 is a subset of A. But it is not correct to say that the set of 1 is an element of A. And also, it's not correct to say that just the number 1 itself is a subset of A, because it's not true. Something can only be a subset if it is already a set. So take a look at problem 2.1 here. We have 3 sets, A, B, and C. Part A, is A a subset of A? Yes, definitely, because 1, 2, 3, 4, and 5 are in fact elements of the set of 1, 2, 3, 4, and 5. Now, is A a proper subset of A? That is not true, because in fact A is equal to A, and a proper subset is a subset that's not equal to it. So that's not true. Part B, is B a subset of A? Well, we can check. Is 2 an element of A, 3 an element of A, and 4 an element of A? Yes, it is. So B is a subset of A. That is true. Is B a proper subset of A? Yes, that is also true because B is not equal to A. Now, part C, is C a subset of A? Now, we need to check, is 3 an element of A? Yes. Is the set of 4 and 5? Is the set of 4 and 5, is that an element of A? No. The elements of A are all numbers. There's no the set of 4 and 5. So that's not true. It's not true that C is a subset of A, and therefore it cannot possibly be a proper subset either. D, is 4 an element of B? Well, yes, 4 is an element of B. Is 4 an element of C? No. There are 2 elements of C. There's 3 and the set of 4 and 5. 4 is not an element of C, even though it's an element of a set that's an element of C, but the set is the element of C, not the numbers themselves there. So 3 is the only number that's actually an element of C, and then we have a set that's an element of C. Part E, list all the subsets of B. Interesting. How many are there? So we need to list all of the sets such that every element in that set is also an element of B. Well, we can have B itself, the set of 2, 3, and 4. We can do the set of just 2, the set of just 3, and the set of just 4. We can do the set of 2 and 3, the set of 3 and 4, and the set of 2 and 4. And we can also have the empty set. The empty set is the set with nothing in it. That is also a subset of B. So you should have had 8 answers. 3 of them are singleton sets, sets with 1 element. 3 of them are doubleton sets, and 1 of them is the entire set B, and the other one is the empty set. So that's 8 total subsets of B. Okay, let's move on to the next page. So there's a few properties to note about subsets. Every set is a subset of itself. The empty set is a subset of any set. If A and B are 2 sets such that A is a subset of B and B is a subset of A, that implies that A is equal to B. And if A and B are any 2 sets, then we cannot have that A is a proper subset of B and B is a proper subset of A. That never ever happens. So let's explain one of these properties now, and you'll be asked to explain the others in the exercises. Problem 2.2, show that the empty set is a subset of any set. Well, the empty set doesn't have any elements in it, so the implication that X is an element of the empty set implies that X is an element of A is true because it never fails. So the empty set has no elements, so every element of the empty set, even there aren't any of them, is an A because there's nothing to check. It's immediately true. It's also known as to be vacuously true, which is a common phrase. It's vacuously true. Also, for any set S, you can have a special associated set called its power set, and we denote it by that curly P of S. So this is a set whose elements are all of the subsets of S. So the power set of S is the set of all sets T such that T is a subset of S. So for example, if S is the set of 1, 3, and 4, then the power set of S, if you look at that, it has the empty set, all of the singleton sets, all of the doubleton sets, and S itself. So notice that the elements of the power set of S, they're all sets, not numbers. And this is perfectly fine. For sets, you can have anything as objects as elements of the set. Okay, and also notice you can take the power set of the empty set. Now, what are all the subsets of the empty set? Well, just the empty set itself. So the power set of the empty set is the set of the empty set. Make sure you understand that. Notice the distinction between the set of the empty set and the empty set. The empty set has no elements, but the set of the empty set has one element, namely the empty set. So let's look at a quick example. Problem 2.3, let A be the set of 1, 2, 3, and 6. That's the set of all positive divisors of 6. We're going to define the set B now to be the set of all S that are in the power set of A such that 1 is not in S. So it might take some getting used to reading this notation, but this means we want all subsets of A that 1 is such that 1 is not contained in it. So if we want all the subsets that 1 is not contained in it, we end up getting the empty set, the singleton set of 2, singleton of 3, the singleton of 6, and then we have the set of 2 and 3, the set of 2 and 6, the set of 3 and 6, and the set of 2, 3, and 6, which is just B itself. Well, no, sorry, that's not, sorry, never mind. But yeah, those are all of the subsets of A that don't contain 1. And notice that's actually, B there is actually equal to the power set of the set of 2, 3, and 6. Okay, so we have some special sets here just so that you know what the name of it is. Z, a bold-faced Z, Z for Zahlen, which is German for integer. This is the set of the integers. Z sub n is the set of 0, 1, 2, all the way up to n minus 1. It's actually the set of integers modulo n, which just means we're just looking at congruence classes modulo n. You don't have to worry about too much what that means. It's just the set of integers from 0 to n minus 1. Q is the set of rational numbers, so all fractions. And notice that in the set of rational numbers, 2 over 4 is just the element 1/2. So we kind of have an equivalence relation there. And the set R is the set of all real numbers, and C is the set of all complex numbers. Notice that we have a chain of proper subsets here. Zn is a proper subset of Z, is a proper subset of Q, is a proper subset of R, is a proper subset of C. And all of those sets are written in bold-faced, blackboard bold, I guess, is what it's called. Okay, and then we have some exercises here. We have 9 exercises. So go ahead and try this now. I'll give you some time to work on this, and then later in the video, we'll pick up on the next page. Okay, hopefully you had enough time to work. Oh, whoops, sorry, there's a 2.2.10 here. I didn't see that. Prove that if S is a finite set and the cardinality of S is n, then the cardinality of the power set is 2 to the n. So actually, I'm going to give you a few minutes to try this problem. Okay, hopefully you got a chance to try that one. We'll go over the answers tomorrow for sure. Okay, next section, operations on sets. So we can take the union of two sets. If we have a set A and another set B, the union A union B is the set of all objects that are elements of at least one of A and B. So we can write this a little bit more formally as A union B is equal to the set of all X such that X is in A or X is in B. Note that our use of the word or does not mean one or the other but not both. Whenever we use the word or in mathematics, it always means one or the other or possibly both. This is the logical way to define or. So elements that are in both A and B are also in the union. Also, for the union, if it helps you picture it, you can have it as a Venn diagram, set A and the set B, and it's just everything in the two circles are colored, including the middle. So we have a few examples there, and take a look at those examples just to see that how the union works. So the union is just taking everything that's in either one of them, or both, as you can see there. So next operation is the intersection. A intersect B. Notice we have kind of a downward cup for the intersection and an upward cup for the union. Actually, in LaTeX, if you typeset mathematics, the union is referred to as a cup, and the intersection is referred to as a cap. So you can think of it like that, I guess. So the intersection of two sets is the set of all objects that are elements of both A and B. So A intersect B is the set of all x such that x is in B and x is in B. X is in A and x is in B, sorry. Some examples down there you can see. The intersection is just the elements that are in both. And notice that if there's nothing in common between the two sets, then the intersection is the empty set. So that's important. Okay. Also notice that the intersection is always a set. So the union is a set, and the intersection is a set. So what you get, it's kind of like doing an operation like plus or minus on numbers. If you add two numbers, you get another number. If you subtract two numbers, you get another number. Same thing with sets. We're talking about operations. So if you intersect two sets, you'll get another set. If you take the union of two sets, you'll get another set. Okay, so hopefully that makes sense. We have union and intersection. Those are two different operations we can do with sets. So now let's have a quick little couple problems to do. Okay, suppose A and B are sets such that A is a subset of B. Problem A is what is A union B, and problem B is what is A intersect B. For part A is a subset of B. If A is a subset of B, then we definitely know that everything that's in A is in B, but we also know that everything in B is also in B. So A union B is definitely a subset of B, and on the other hand, every element of B is also an element of A union B. So B is a subset of A union B. Hence, A union B is equal to B. So this is super important here. If A is a subset, if we just have two sets, no matter what they are, if X is a set and Y is a set, X being a subset of Y and Y being a subset of X, if both of those things are true, then X is equal to Y. So that's the way that we show that two sets are equal. So here we have that A union B is a subset of B and B is a subset of A union B. Therefore, A union B is equal to B. So the answer to part A is just B. And similarly, the answer to part B is just A. Because if something is in both A and B, then we know that it's in A. And everything in A is going to be in A intersect B, because A is a subset of B. Okay, hopefully that makes sense. And then there's this important box here. That's exactly what I just said. So to show that two sets are equal, we have to show that one is a subset of the other and the other is a subset of the first one. And we have to show that both are true in order to show the equality. So definition, if A intersect B is the empty set, then we say that A and B are disjoint sets. And here we have a nice visualization of A union B and A intersect B. Now if the sets A and B are not disjoint, then they'll look like this Venn diagram. And A union B is everything shaded, and over there, A intersect B is just the intersection in the middle. Now, if A and B are disjoint, then A intersect B is the empty set. So, one thing to note, these two operations of intersection and union, they distribute over each other. And that's a very interesting fact, I think, about sets, is that not only can we, the union operation and the intersection operation, they have distributive laws, like this. So problem 2.5, prove that if A, B, and C are sets, then A intersect parentheses B union C is equal to what we get when we use the distributive law. So just like multiplication distributes over addition, we have that intersection distributes over union in exactly the same way. So that's kind of interesting. And in the subject of abstract algebra, we can actually generalize this, and we'll see exactly what's going on with that, but we won't study that in this course. But also just a side note, the reason we're studying a little bit of sets set theory is that it's important for probability later on. So yeah. So if we go ahead and we want to prove that these two sets are equal, now remember, the left side of the equal sign here in this problem 2.5, the left side is a set, right? B union C is a set, and A is a set, so we can take the intersection of the two. A intersect B is a set, A intersect C is a set, so we can take the union of those sets and get another set. So it definitely makes sense to have the equal sign there. Now to show that equal sign is true, we need to show that the set on the left is a subset of the set on the right, and vice versa. So here's how this proof will kind of go. Suppose X is an element of the left set there. It's an element of A intersect B union C. Now since X is an element of that intersection there, then X is going to be an element of A, and X is going to be an element of B union C. That means that X is in A, and X is in B, or X is in C. Now if you've studied logic before, you'll know that the AND, or you might not know, you might have forgotten, but the AND binary operation distributes over the OR binary operation, and vice versa. So this kind of boils down to logic. We have that an AND or an AND is actually the same thing as an AND distributing over an OR. So that's kind of how we show that. We have to show the opposite direction as well. If we know that Y is an element of A intersect B union A intersect C, well, then Y is in A intersect B, or Y is in A intersect C. Equivalently, Y is in A and Y is in B, or Y is in A and Y is in C. And logically, the distributive law holds there. Cool. So those two things there, those two facts together imply that the two sets are equal. Now, the logic steps in the middle of the above argument might be a bit unclear. Definitely in the next section we'll cover some more logic rules, but we can actually visualize this theorem by Venn diagrams. So since there's three sets involved, we can have three circles there. They all intersect each other like that. And you can see that the left side is exactly the same as the right side, just by seeing the shaded parts there. Yes, and then right here you can see the right side, how the right side is those same sections on the left side. So there's visual evidence that the two sets are equal. And just note that using Venn diagrams is not technically a proof, but you can, I guess, sort of justify it that way, but it's not an airtight proof. Okay, so now let's talk about the idea of a universal set. That is just going to be the set that contains all possible elements in a given problem or situation. So in an introductory algebra setting, the universal set might be R, the real numbers. So for example, the set of x such that x squared plus 1 equals 0 would be the empty set, because it assumed that we're only working in the real numbers there. However, on the other hand, if the universal set were the complex numbers, then that same set would be the set of I and negative I. So the universal set may vary from problem to problem, but it's basically just the set that is relevant to the problem. And pictorially, the universal set is usually denoted by just a big rectangle, and any other sets that are relevant to the problem would be inside of that rectangle. So we have our big universe, and this actually allows us to talk about set complements, which we will in a bit. So yeah. So in any context in which we have a universal set, we have the implicit assumption that every set under discussion is automatically a subset of the universal set. In other words, we're not allowed to go outside the box of the universal set, because by definition the universal set is just everything possible in the problem. And it's not really a nice set. I mean, it's not really a preferred set to use. Unless the context is very like demanding of it. So okay, so on this next page we'll talk about the complement. So if we have a universal set U and we have a set A, the complement of the set A is everything that's not in A but is still in the universe. So the picture should make it clear what it is. The complement is everything but what's in that set. So if the universal set is the real numbers, and we're talking about the set of integers, then the complement of the integers is the set of all decimals, basically, terminating or non-terminating. So here we also can talk about the set theoretic difference. That is an operation for sets. So here's another operation. If we have the set A and a set B, the set difference is going to be the set of all, like A minus B or A slash B is going to be the set of all objects that are in A but are not in B. So I'll give you a few minutes here to do these exercises here, 2.3.1 all the way through 6. Yeah, and then we'll get started on a little bit more truth and logic. So just so that you know, a statement or a proposition is an assertion that is either true or false. So in mathematics, we only deal with statements that are true or false, but not both, right? So like paradoxes or just contradictory statements, things like that, all like kinds of ridiculous statements you could come up with that seem like they are both true and false or they're neither. We're not going to deal with those. We're just going to deal with propositions that are either true or false. Okay, so I'll give you a little bit of time to work and then we'll go to the next page. Okay, so yeah, so statements, they're just things that are either true or false. There's several statements here on the page. Um, Now, there are certain types of statements that are called quantified statements, and that's when we say something about all objects of a given category. So, if we say all even integers are divisible by 2, the word all implies that this is an example of a quantified statement. And we'll talk more about that in the next section. Also, the phrase there exists is also another quantified statement. If we say there exists an integer whose square is 7, that's a false statement, but it is a quantified statement because we're talking about the existence of something. So there's a few examples of things that are not statements, mathematically speaking, and you can look over those. And then there's also something called a compound statements. Now, compound statements are something where we can like make up a bunch of simple parts. So the negation of a statement, where we have a little tilde in front of a statement P, that statement is true when P is false, and is false when P is true. So the negation of P is the opposite of P. They have opposite truth values. For example, if P is the statement Paris is the capital of France, then not P would be the statement Paris is not the capital of France. And then the conjunction of two statements is the and, basically. So P and Q. So if P is Paris is the capital of France and Q is Madrid is the capital of Spain, then P and Q is Paris is the capital of France and Madrid is the capital of Spain. The statement P and Q is true provided that both P is true and Q is true. Otherwise, P and Q is false. Okay. The logical disjunction is the or statement. So there's a warning here, P or Q. Now this is the inclusive or, meaning that in mathematical logic, or means that it's either one or the other or both. So it means that at least one of the two is true. So these terms conjunction and disjunction are not the most important part. You just need to know what and, or, and not mean. And now we can talk about what's called a truth table. A truth table is simply, it lists all the possible values of a compound statement given the possible values of its component parts. So for example, we show the truth tables of our basic operations. Not P there. P can be either true or false, and so we have what not P is, depending on what P is. And then we have P and Q. Now, since there's two variables involved in the expression P and Q, we need 4 rows of truth values here, because we have 4 possibilities for combinations of truth and falsity for P and Q. So we have true, 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 false, false, true, and false, false. And then we have whether P and Q is true based off of the truth values of P and Q. And we do the same thing for the or. Okay, so a quick problem here. Prove that for any statement P, the statement P and not P is always false. So the way you'd prove this is by drawing a truth table. So first, we know that this statement must be false just by common sense. It's a contradiction, meaning it's always false. There's no way that a statement and its opposite can both be true, but we can prove this by drawing a truth table. So the truth table here, we have the 2 possible values for P, true and false. Then not P has been false and true. And then if we do the and symbol on true and a false, we'll get a false. And if we do the and symbol on a false and a true, we get a false. So from the table, any input value of P makes the statement false. Now here's a little more complicated example. Prove that for any statements P and Q, the statements P or Q and not bracket, not P and not Q are either both true or both false. And there is a logical symbol called the biconditional that you could use for this. But if you're not familiar with that, all you'd have to do here is draw a truth table such that you have the column for P or Q all done, and that you have the column for not bracket, not P and not Q all done. And you have to you just have to observe that both of those columns are identical. That is actually an example of one of De Morgan's laws, and it's actually um, it's the fact that the negation of P or Q is equivalent to not P and not Q, and the negation of P and Q is equivalent to not P or not Q. And De Morgan's laws will be something you can prove in the exercises. But next, let's talk about implication. So logical implication is read if P, then Q. So it just means if P is true, then Q is true. And a little arrow is denoted to use implication. So we read it as P implies Q. So this is always true unless the formula before is true and the formula after is false. So P implies Q is only false when P is true and Q is false. So for example, look at this little green box down here. Here's a bogus claim. 4 is an even number, not an odd number, and 10 is composite, not prime. So the statement, if 4 is an odd number, then 10 is prime, is a false statement. This is totally incorrect logic. 4 is an even number, so if 4 is an odd number, then 10 is prime is true. So if is an implication, if the if part of an implication is false, then the implication is automatically true. So in other words, if we have an if-then statement, if the if part is not satisfied, then it's automatically true. Okay, let's take a quick look at the truth table for the implication. Again, we have P implies Q. The truth table for that will have 4 rows because we have 4 possible combinations of truth and falsity for P and Q. And notice that in the truth table, the only false row is the second one, where P is true and Q is false. And they do introduce the biconditional here. Okay, so P biconditional Q, that is where you have a double arrow pointing both ways. That's a logical operation that's a shorthand for P implies Q and Q implies P. So in other words, we could write P if and only if Q. So the term if and only if is the same thing as the biconditional, which is the same thing as the two-way implication. And there's a truth table for it. We have a column for P, a column for Q, column for P implies Q, and a column for Q implies P. So then we just use the logical conjunction on those two columns, to get the last column. And we see that P biconditional is Q whenever P and Q have the same truth value. So problem 2.7, prove that for any statements P and Q, the statement P or Q biconditional, not parentheses, not P and not Q, is always true. So you'll have to draw a truth table for that. So that's part of your homework. So there's 2 important logical operations that we can do with implication. The first is to take the converse. The converse of the statement P implies Q is the statement Q implies P. So notice Q implies P and P implies Q. They're not at all opposites. They're completely different statements. They're not opposites of each other. They're completely different. So the truth values of them aren't necessarily related. One more important logical operation is the contrapositive. So if P implies Q is true, then not Q implies not P is also true. That's called the contrapositive, and it has the same truth value as the original implication, contrary to the converse. And the contrapositive is important because, like I said, it has the same truth value as the original implication. So when we're trying to prove an implication of some sort, a lot of the times it's much easier to prove the contrapositive, and that's equivalent to proving the original implication. So you'll definitely want to keep that in mind. Now, I'll give you some time to prove these, to do these exercises. And here I have a few more exercises to do and to turn in as homework. All right, so let's talk about quantifiers now. Most statements that we're going to work with depend on one or more quantifiers. For example, the statement all even integers are divisible by 2. The words all and there exist and every, words like that, talk about or means that there's going to be a quantifier associated with them. There's two types of quantifiers. There's the universal quantifier and there's the existential quantifier. So you'll definitely want to write that down. There's two types of quantifiers. And we'll study quantifiers in depth in the set theory course later, in the third session, which I think a couple of you are enrolled to take that currently. So there's a universal quantifier. That's when we talk about things like all even integers are divisible by 2, or every or all. And then there's the existential quantifier, and the existential quantifier is associated to statements that talk about the existence of something. So the existence of some object. There exists an integer x such that blah blah blah. And yeah. So the two quantifiers, they look like this. The universal quantifier is an upside down a, and we can read the following thing here. For all x in z, 2 divides x, or x is divisible by 2. The little straight line there can sometimes mean divides. It's just a shortcut for it. So that's how we read it. For all x in z, 2 divides x. Now, the existential quantifier is like a backwards e. So this little sentence right here says, there exists an x in z such that x squared minus 5x plus 6 is equal to 0. So that means there is some element of z that makes the statement true. That's what the statement is saying. So if S is a set and P of x is a statement that depends on an element x of S, then we have for all x in S, P of x, right? That right there, that means that P of x is true for all elements x of S, and there exists an x in S, P of x. That means that P of x is true for at least one element x of S. Now, the symbols aren't that important. You won't see them too often, but the meaning of the quantifiers is super important. You will see the symbols often in the set theory course, but in this course, no. It is very important to understand the difference between a statement being true for all elements of a set and merely that there exists an element of the set that makes the statement true. There's very different situations there. For example, the statement all triangles are equilateral is clearly false, but the statement there exists an equilateral triangle is clearly true. So we can combine quantifiers in the same statement. For example, for every positive real number x, there exists a positive real number y such that x equals y squared. Where there we have two quantifiers in the same sentence. That's perfectly allowable, and we'll see that often. Now, that statement that we just said, for every positive real number x, there exists a positive real number y, such that x equals y squared. If we wrote that symbolically, it would look like that, but it's not super important for you guys to be able to write down statements symbolically. Just know that the order that we write the quantifiers in is incredibly important. It'll change the meaning entirely if you switch quantifiers. Just for example, if we say that there exists some positive real number y, such that for every positive real number x we have x equals y squared, that's saying a completely different thing than the thing above, right? We switched the quantifiers, but it resulted in a completely different statement entirely. Okay, lastly, we need to know how to negate quantifiers. Okay, so when we want to negate a statement that involves a quantifier, we got to be careful to also reverse the quantifier. For example, if we want to negate the statement all cars have 4 wheels, the opposite of that statement is there exists a car that does not have 4 wheels. Make sure you understand that. In the first statement, all cars have 4 wheels, so to get the opposite of that statement, we don't need that all cars don't have 4 wheels. We just need some car without 4 wheels, right? So another example is there exists a person from Canada who plays hockey. The opposite of that statement is all people from Canada do not play hockey. Make sure you understand that. So symbolically, if p of x is a statement that depends on a variable x, that's an element of a set S, then the opposite of the statement for all x and s, p of x is true, is there exists an x and s such that p of x is false. So to prove a universally quantified statement, so that means that there's a for all in there, a statement that is true for all x and s, you must prove that the statement is true for every x in the set S. On the other hand, to prove an existentially quantified statement, a statement for which there exists an x and s that makes it true, you only have to find a single x in the set S that makes the statement true. Okay, so those are exercises for you to do for homework. Okay, and we have a nice summary here for what we learned today. We've learned about these concepts of set theory and basic logic. We've learned about what sets are and how they can be described, how sets are related to their subsets, the empty set, the power set of a set, how to combine sets by union and intersection, the basics of truth and logic, statements are either true or false, the meanings of and, or, and not, the meaning of an if-then inference, the converse and contrapositive of an inference, the meanings of and difference between for all and there exists, okay? And now here's some review problems. So we have this 2.8 problem here. We're saying let S, D, P, U, V, and W be those particular sets, and then there's going to be some problems on the next page. So that'll be homework for today. So the rest of the problems that you see on the screen are going to be all your homework. So we have 2.8, and now we'll go to the next page. So these are all homework problems, and these are all homework problems. So you can just pause the video in those spots.